4 billion years ago, the Earth was a violently churning ocean of liquid rock suspended in a freezing vacuum. During this molten youth, gravity acted like a sieve, pulling heavy elements, iron, gold, platinum, down into a dense core. This migration left the cooling crust stripped of metals needed for industrial infrastructure. Yet, we construct towering cities of steel and route our global communications through delicate gold wiring. For humanity to gain access to these resources, a different geological process had to intervene. The material foundation of our modern technological civilization is the result of a specific geological anomaly. Long after the crust solidified, the planet was subjected to the Late Heavy Bombardment, a period of relentless, punishing asteroid impacts. These collisions reinfused the sterile outer rock layer with deep space iron, cobalt, and precious metals, seeding the planet with the exact materials we mine today. We have spent the last few centuries aggressively scraping away at this finite alien deposit. Now, we stretch those reserves to their physical limits, tearing through ecosystems to find whatever remains. Looking outward for more materials introduces a brutal physics problem. Earth's gravity demands an enormous toll to let anything leave. Launching even small payloads of fuel or building supplies off the surface requires thousands of tons of volatile propellants and massive infrastructure. We cannot afford the energy cost of dragging terrestrial materials into orbit to build our future. To expand outward, we must return to the rocks that originally delivered our resources. Millions of near-Earth asteroids orbit our sun. They are preserved time capsules, holding the same raw materials that coalesced to form the solar system. The primary targets fall into two categories. C-type asteroids are carbonaceous bodies packed with ancient frozen water. M-types are the exposed, metallic cores of dead protoplanets, rich in iron, nickel, and platinum. Intercepting them is a proven reality. In 2020, NASA's OSIRIS-REx spacecraft successfully navigated to a carbonaceous asteroid named Bennu, touched down, and secured physical material. The probe extracted rocks and dust directly from the vacuum of space, encapsulating the primordial dirt for the long journey back to Earth. When that capsule parachuted into the Utah desert in 2023, it demonstrated that recovering material from deep space is a matter of terrestrial engineering. With scientific feasibility confirmed, commercial startups are moving to scale this process into a private industry. Mining in microgravity defies traditional methods. If you press a drill into a rock where there is no gravity, the physical force simply pushes your spacecraft backward. Asteroid Mining Corporation tackles this by developing SCAR-E, a robotic system equipped with specialized mechanical grips that anchor its legs directly to the rock, stabilizing the machine for excavation. TransAstra avoids drilling entirely. Their optical mining method envelops a C-type asteroid inside a sealed inflatable bag, focusing the sun's rays directly onto the rock. The extreme thermal heat bakes the asteroid, causing trapped ancient ice to sublimate into water vapor. That vapor is collected inside the bag without ever cutting into the stone. Astroforge targets M-type asteroids, aiming to bypass water and refine high-value platinum group metals while floating in the absolute vacuum of space. Each company utilizes different mechanics to solve the exact same physics equation, extracting raw material in an environment devoid of Earth's rules. The goal is not to haul mountains of platinum back to Earth. Doing so would oversupply the market and crash global commodity prices. This flowchart illustrates the real economic model, in-situ resource utilization. It compares the financial penalty of launching mass out of our gravity well against the efficiency of using materials that are already in zero gravity. Water extracted from C-type asteroids can be split into hydrogen and oxygen to produce rocket fuel directly in space, while metals from M-types are refined to construct orbital habitats and satellites. These materials serve as the physical scaffolding for a self-sustaining space economy, functioning as the foundational infrastructure of an orbital civilization. The metals in our smartphones and skyscrapers began in the molten chaos of the early solar system, drifting through the void before raining down to build human civilization. By harvesting these elements at their source, we eliminate the need to drag our planet's resources into the dark. We turn the solar system into an open shipyard. We are composed of the same dust and gas that we are now learning to capture and refine. Harvesting the same elements that seeded our world allows us to close a 4 billion-year cycle, By returning to the asteroids, we establish a permanent, self-sufficient presence among the stars. Millions of miles from Earth, the first phase of an off-world industrial economy is silently moving into position. Real-world startups are moving past the theoretical stage and into the field, with actual extraction test missions currently on the launch manifest for this decade. Traditional mining concepts are useless here. Forget the massive open-pit quarries, the heavy excavators, and the high-torque drills that define resource extraction on the surface. On Earth, gravity provides the weight and friction required for machinery to grip the ground. It is the invisible force that allows a drill bit to bite into rock rather than simply spinning in place. Near-Earth asteroids offer no such help. These bodies are so small that they possess virtually zero gravitational pull. Our entire industrial history was built around the constant downward force of gravity. In the deep space environment, that lack of weight makes standard terrestrial mining methods physically impossible. This schematic illustrates a fundamental physics problem, Newton's third law. In zero gravity, drilling a rock creates an equal opposite force, propelling the spacecraft away. Furthermore, drilling fractures the rock, creating an expanding cloud of static-charged regolith particles that grinds down delicate solar panels. This image of an Apollo astronaut shows the reality of that material. Lunar dust is highly abrasive. It degraded mechanical systems and ate through the seals of suits during every mission to the moon. In a deep space environment, there is no way to clear a jammed joint or clean a solar array. A single dust cloud can effectively end a multi-million-dollar mission in seconds. Space mining presents a unique engineering challenge. We need to pull heavy resources out of a rock that we cannot safely touch or push against. Modern space startups avoid the complications of kinetic drilling by integrating the space environment directly into their engineering. Trans-Astra targets C-type asteroids, which are rich in frozen water. They use a robotic spacecraft to deploy a translucent inflatable membrane, completely swallowing the jagged rock to seal it in a controlled environment. The craft uses parabolic mirrors to catch raw sunlight, focusing those beams into intense, targeted points of heat directly on the captured asteroid surface. As temperature climbs, trapped ice vaporizes without physical digging. The water gas is collected and condensed into orbital storage tanks. Harvesting this water creates off-world fueling stations. It turns these floating rocks into the critical infrastructure needed for long-distance interplanetary travel. Extracting solid metals requires a different approach. Before any mining can begin, engineers have to solve the problem of anchoring a spacecraft to a surface that has no weight. Asteroid Mining Corporation is developing the SCAR-E robots for this environment. These units use specialized mechanical claws to grip and walk across the rock, providing a stable platform for drilling. Other missions use kinetic harpoons. A projectile pierces the asteroid's surface, allowing the craft to use tension cables to winch itself tightly against the rock. The ultimate targets are M-type metallic asteroids. However, returning a massive iron-heavy rock to Earth is economically impossible due to the sheer weight of the material. Astroforge plans to process the material on site. They utilize the absolute vacuum of space to mechanically refine platinum group metals, separating the valuable minerals from the waste rock while still in orbit. This image of a recovered capsule shows the benefit of that process. By refining the ore in space, the company only returns a small, high-purity payload that is easy to manage during re-entry. By leaning into the unique properties of vacuum and microgravity, these startups turn the environmental hazards of space into functional extraction tools. This targeted approach is a sharp departure from the broad, high-profile failures of the 2010s. Companies like Planetary Resources, seen here, raised massive amounts of capital for ambitious goals that the technology of the time couldn't yet support. The primary change is represented by this SpaceX launch. Commercial rideshare rockets have lowered the cost of getting into orbit so significantly that sub-$20 million mining missions are now financially viable. Modern probes further reduce costs by using off-the-shelf components and autonomous optical navigation. They don't require the custom billion-dollar engineering or the massive ground teams of previous eras. The ultimate aim is to migrate heavy industry and resource extraction off Earth. If the most destructive parts of our economy move into space, we can reduce the industrial burden on our own biosphere. Asteroid mining is moving into its industrial phase. This is the foundational infrastructure required to support a permanent human presence beyond our own planet.